Hey everyone, I'm Raiaan from Roots of Unity, and today, as a part of our continuing topic on trigonometry, we're going to cover inverse trigonometry and look in depth at curve sketching. We will also look at some practice questions as per usual. Firstly, let us try to recall the trigonometry graphs we looked at in my last video. I'll give you a moment to try and remember the general shapes. So, the cos curve is a wave starting at 1 and heading down to -1 at pi radians and then going up again. The sine curve has a similar approach, but starting at 0, going up at pi by 2 and then down again. Both the curves have a period of 2 pi and a range of -1 to +1. Meanwhile, the tan graph is a bit different, as the curve goes from 0, approaches infinity at pi by 2 or 90 degrees, and starts again from negative infinity after the asymptote. The tan graph has a period of pi or 180 degrees. Now, I'll give you a moment to consider what the inverse functions of these graphs would look like. Keep in mind that the inverse only applies to one-to-one functions, which gives us a restricted domain to work with. Otherwise, the dotted lines would result in a one-to-many function. So, these are what the graphs of sine inverse and cos inverse look like. Here, the domain and range of the inverse functions are flipped from their counterparts. Cos inverse has a domain of -1 to +1 and a range from 0 to pi. Sine inverse also has the domain -1 to +1, but in this scenario, the range goes from -pi by 2 to +pi by 2. The inverse graphs are basically reflections across the line y equals to x. In the case of the tan graph, the domain here is restricted from -pi by 2 to +pi by 2, so basically within the asymptotes. You should have an idea of what the inverse graph for this looks like. Once again, this is reflected across the line y equals to x. In this case, the domain extends from -infinity to +infinity, and the range is from -pi by 2 to +pi by 2. Before we move on, here's a question for you guys. What would the graphs for the reciprocals look like? That is, the cosec, sec, and the cot graphs? Try to think of the graphs yourself. We'll go over them in the next video. Now, we'll take a look at something you encounter quite often in trigonometry. That is curve sketching. Here's an overview of what the equations may look like and how you approach the general shape. Firstly, the value right next to trig identity would determine the amplitude. You could compare it to scaling. In a general cos or sine curve, the range goes from -1 to +1. Here, if a equals to 3, the range gets tripled. The values of the maximum and minimum heights get extended thrice in both ways. Next, the b here determines the number of cycles. You'd normally complete one cycle within the period 0 to 360 degrees. Say, if b equals to 2, you'd complete 2 full cycles before reaching 360 degrees. If b was 0.5, we'd complete half a cycle within that interval. While we are on the topic of angles, if we add a value c to the angle, the curve gets shifted. If c is negative, it goes to the right, and a positive c makes the curve go left. Similarly, next up we'll take a look at d, which signifies a shift in the y direction. This one's easy to recall. A positive makes the curve go up, while a negative makes the curve go downwards. Lastly, don't forget to check the sign before the sine or cos segment of the function. If the sign is negative, the curve gets flipped horizontally. If you have time on your hands, I'd still suggest plotting. Just choose the values to input effectively. Moving forward, it's time to look at some examples. I have gone through a very detailed solution of a curve sketching question, and I hope it'll help clear your concept. Take a look at the question carefully. Firstly, we can draw the basic shape of a sine curve as follows. Next, we multiply the curve with 2, which doubles the amplitude. The values at y equals to 0 stays the same. Then we multiply x with 3, which means the curve completes 3 cycles within the interval 0 to 2 pi. Subtracting pi by 2 shifts the curve to the right by pi by 2 radians. Then, adding 2 to the sine expression shifts the curve upwards, bringing us to the final equation. It's fun to see how much the curve has changed from what we initially started with. Don't get overwhelmed with the number of steps shown here. Usually they're unnecessary, but they give you a step-by-step visualization of what exactly you're dealing with. The following question contains multiple parts, tying together what we've learned so far. Firstly, we'll make use of trigonometric identities to rearrange the function according to the equation. If you want to save time, consider substituting sin x with s, cos x with c, and tan x with t. Just make sure the angles for them are all the same. When we express the equation in a given format, the shape becomes much clearer. In part 2, we equate the function to 7 sin x and rearrange to find the solutions. We obtain the roots 1 by 2 and 3, and we know 3 is out of the question here. Then, by utilizing the symmetry properties, we find the solutions within the given domain. Lastly, we're asked to find the range. Here, it's useful to keep in mind the range for a normal sin square x graph. Starting from a sin x graph, we can see that the range shifts to the positive part only since sin x gets squared. Now, going back to our question, we assume the sin square expression to equate to 0 and 1 respectively. By adding or subtracting 5 and 3, we can deduce the range. Now, if the question here asks you to state the intervals with no solutions, you'd write fx is less than 3 or fx is more than 5, not greater than or equal to 5. In the next problem, we'd make use of multiple parts yet again. First, we'll construct simultaneous equations with the given information. This will easily let us find the values of a and b. In part 2, we equate the function to 0. Since cos is positive in this scenario, we find the values in the first and fourth quadrants. Lastly, we sketch the equation. This can be done in one step, since we know the general shape of the curve and the values are given for 0 and pi by 2. It's flipped horizontally and crosses the x-axis as 0.36 and 2.78. So far, we've only seen how to sketch graphs. Now we'll take a look at how to interpret them. Here's a graph where we'll have to find out a, b, and c. We know that a corresponds to the amplitude, so it's pretty obvious that the value is 6. The curve completes 2 cycles in the interval, so the value of b would correspond to 2. And lastly, since the curve has been shifted 3 units up from the x-axis, the value of c is 3. When we find the smallest value, we consider the one closest to the lower limit of the interval. The basic acute angle is pi by 6, and since sine is negative, the solutions lie in the third and fourth quadrant. We take the value in the third quadrant, is 7 pi by 12. The next question is very easy. We'll equate the two curves here like we'd solve any other equation, and make use of identities to rewrite the problems in terms of sign. We solve for the roots using the quadratic formula, using the positive root. The negative will give you an error. There is no need to solve further since this part only asks for the x-coordinate of a. In the second part, however, we find the other solution, which is 2.475. We insert that in any of the original equations and hence find the coordinates of b. Lastly, we'll refresh what we learned about inverse functions in the beginning of this video. Try and find the domain and range of the following equations. I'll give you a moment to try and do this yourself. So, these problems look very messy at first, but what we do here started off by rearranging, making x the subject. We already know that for inverse sine functions, the domain is from -1 to +1, while the range goes from -pi by 2 to +pi by 2. We'll make use of these to answer the following questions. Here, the domain stays the same as we're not adding any other number to the sine component. As for the range, we equate the entire angle to the highest and lowest values, and then rearrange for y. As easy as that. We did a similar procedure in the second question. After rearranging, we see that 4 gets added to the sine component. Here, we take the minimum and maximum values of the sine component from the domain and solve accordingly for x. We use the same procedure as used previously for finding the range, and we're done discussing the problems. Once again, thank you so much for watching this video. In the next part, we'll go over the trigonometric reciprocals and then we'll focus on more identities. Hope these videos have been useful. Bye.